Antonio. So yes, indeed, since this is a basic SIDC seminar, I simplified the title and I simplified most of the presentation, so this should be enjoyable. Sit back, relax. We'll also skip the abstract. So what we are going to do today is to go back to where Matt introduced the solar corona. We'll quickly touch it again, why the solar corona is worth looking at. And then we will focus more on instrumental aspects. Here at the Observatory, we have been very busy with two types of instruments, coronagraphs and EUV imagers. These are very different sorts of telescopes to look at the corona. And so I will touch upon what the differences are. And in the fracture zone of the capabilities of both types of instruments, there is what we will call the gap. And in that gap, interesting stuff happens. So in point 5, we will briefly look what to do with this. What are the opportunities and our future projects, how will they contribute to that? So start with the corona. The solar corona, what is it and why should we care about it? This is an image from the eclipse of last year in Northern America, middle of August, from Williams College. And I've never seen an eclipse myself, but what people tell me is that it's amazing, it's inspiring, it's very beautiful, and it's so big. And in fact, indeed, that's surprising that it's so big if you think about it. The solar radius is 696,000 kilometers, or about 700 what we solar physicists call megameters. And you see from this image that the corona is easily another solar radius higher than that. Of course, you have to see it in relation to the object, but even then it's amazingly big. If you think about it and you do a bit of formulas, in a vertically stratified atmosphere where gravity pulls the atmosphere down and gas pressure pulls it up, if you make a bit of calculations of that, you get the obvious answer that the density or the pressure of the atmosphere is exponentially decaying as you go higher in the atmosphere. And this exponential decay comes with a characteristic length scale. It's called H there. And this length scale gets thicker, the atmosphere gets thicker when it's hotter, and it gets smaller when the gravity is higher. It's all intuitive, of course. If you fill in numbers for the Earth into that, you get a length scale of 9 kilometers, which is kind of correct, because if you stand on Mount Everest, the atmosphere is about a factor E less dense than what it is here. So the formula makes sense. So now we apply it to the sun. We fill in the gravity of the sun way higher. We fill in this M, the atomic number of the particles, which is mostly hydrogen there. We fill in the surface temperature, and we get a thickness of a few hundred kilometers. Now, a few hundred kilometers, I cannot even plot that on this graph. It's completely invisible. And even if you're off by an order of magnitude or 2, it would still be invisible. So the corona is way thicker than it's supposed to be, knowing the surface temperature and the gravity of the sun. Already, this thing, just looking at the eclipse, tells us that the corona cannot be that temperature. It has to be much hotter. If you fill in millions degrees, then you get about this thickness. So the corona is not at the temperature of the surface of the star, the sun, but way hotter. And in fact, the same information can be learned spectroscopically. In the beginning of the 20th century, this was still a big enigma. They took eclipse light, send it through a prism, and then you get all these colored suns, one after the other. The red sun being a spectral line from hydrogen, and then there are other spectral lines. I don't know all of them, but it's known atoms, carbon, calcium, and others. And there was this green sun there in the middle that nobody knew about. It could not be related to anything we knew about atomic physics, beginning of 20th century, until this bright person, Bengt Edlin, identified it as iron that was ionized 14 times. So this again gave proof that the corona is very hot and that there is not such an element as coronium that we still have to learn about. So to me that is all very interesting. I can connect it to physics. the corona is big and hot and interesting, but actually, why would we care about this? And I collected 3 answers to that, and the first one is that the sun is a star, but it's the only star where you can spatially resolve the atmosphere. It's the only star that you can actually see in some detail. So what we learn about the sun can be applied to other atmospheres of other stars. Also, you already saw it with the spectra. In the process, while studying it, you learn about atomic physics. It's all plasma, so you learn about plasma physics, and God knows, perhaps we can apply it and run a nuclear fusion reactor on Earth with the same equations or the same physics that we've learned. More recently, or it's at least a more recent hype, is that the influence of this solar activity comes through the corona to us. So the source of space weather is actually there in the corona. So I think the corona is worth studying, and so you need instruments to study it. The instrument to, the name says it, the instrument to observe the corona is a coronagraph. So why is it actually so hard to image the corona? And I must admit, I never had any formal training in optics whatsoever, not even a course. So this is what I learned on the way, and therefore very simple. On the top right there, you see my simplified telescope with an aperture, a lens, and a focal plane, the red thing where I put my camera. And I plotted here 2 beams of light. One, the yellow one, coming from a feature on the solar disk, and one, the green one, coming from a feature in the corona. And so there will be many more features, many more beams, and the whole red focal plane there is filled with features that we can image. Now the problem is that the orange beam is 1,000,000 times brighter than the green beam. The sun is really bright as compared to the corona. And so if you just point your regular telescope to the sun, assuming you don't burn it, the thing that happens is that just from the diffraction of your aperture, you get all kind of signal all over the place, a haze that fills your complete focal plane. And so that haze will be way brighter actually than your green beam. So you cannot image the corona like that just because of the diffraction and the haze from the sun itself. I'm saying diffraction of the aperture, but it's also little dust or imperfections in your lens, or anything that is not absolutely perfect in the whole optical system will create a haze that completely blurs your signal. So that doesn't work. Now, of course, there is the Earth atmosphere also on top of that makes it even worse. But if there is an eclipse, the moon gets in front of the sun, then it works spectacularly, and you're left with the usual problems of the Earth atmosphere, but you can actually make these beautiful images of the eclipse. So that works. So clever people thought, let's do an artificial eclipse then and put in something that blocks the light of the sun. It's called an occulter, in this case an external occulter. It's an occulting disk outside the telescope, and it's held by a little arm that puts it in front of the telescope, and we see what happens then. Of course, the sunlight itself is blocked or mostly blocked, but now you get diffractions on the edges of this occulting disk. Also, since your arm is necessarily of a length comparable to your telescope or a bit longer, say a meter or so, you also block a lot of the signal from the corona. So while you still have the haze of the diffraction, not only of your lens now, but also of the occulting disk, your signal goes down also. So that is not a solution in itself, although if you do it cleverly, it can help. It's part of the solution. So people have been elaborating on this. The longer the arm is, the better it gets. You could have several of these occulting disks, one after the other, and each next one being a bit bigger than the previous one, so it captures most of the diffraction light of the previous one, and so on and so on and so on. But it's not a solution in itself. Let's go back to the problem at the bottom there, where you have the full light entering your lens, and you get this diffraction haze from your aperture. And we look at the telescope that people have built behind it. So instead of the red focal plane on top now, people have taken that out. They attach another tube to the initial telescope, and where the focal plane used to be, we put another occulter, another disk. It's called now an internal occulter because it's inside your telescope. The image that comes from the sun is now projected on this black disk and is lost. This light is absorbed, and you got rid of that. The light from the corona still focuses on the same plane, but since you're not capturing it, it's a diverging beam behind it, and with proper lenses you can again focus that a bit further on in a focal plane. So that's recovered, nothing lost there. What you still have is this haze that came from the diffraction of the aperture, right? And that diffraction, that aperture is now captured in the second lens and focused on yet, say, another occulter, but now it's called Leo spot. Leo because Leo is the guy who invented it. And so with this combination now of an external occulter, an internal occulter, and then this Leo spot and stop, it's a bit confusing, I always mix them up. This combination is what makes a coronagraph. And different implementations of coronagraphs have variations on this theme, but it's essentially that there are also coronagraphs without an external occulter, and then it gets a bit more tricky inside. But it's always a combination of these things. So that's a coronagraph. That's the guy who invented it, Bernard Leo, working here in Pic de Midi. And on the top right, you see an image which such an instrument can produce on the ground. So this is not from Pic de Midi, it's from HAO in the United States. And the truth is that from the ground, coronagraphs don't work very good because of the remaining diffraction in the Earth atmosphere. It's normal, you have this bright sky that is sending in light in your telescope from all possible directions. That doesn't help. So what you really want to do is take this sort of instrument and bring it into space. That's what people have been doing over many years. I don't want to go into details, that's a talk in itself. But in the end, we ended up with the so-called LASCO coronagraphs on the SOHO ESA NASA mission. What you're seeing here are actually two coronagraphs, the blue and the red separately, which we have put together into one frame to give a more complete view. And so what you see in the middle is this black disk, that's the occulting disk where you have no signal. The black ray in the top right is this arm that holds the occulting disk, so you cannot have signal from there, or not very much. And you see the corona. These features that you see flowing out are coronal mass ejections. Unfortunately, in this movie, there is also the software detection on them on top of it, but ignore that for a moment. You see stars and planets. That's all very interesting. And so this is a solution. You can now see eclipses more or less similar to natural solar eclipses, but with an instrument if you put these coronagraphs into space. Now the annoying thing, of course, is the occulting disk. The source, the center of the object is missing in these images. You can't see the sun, and you cannot see how this corona connects to the disk. And that's where coronagraphs cannot go much further. And we need a new technology. So to go back, or to introduce that, we need to go back a little bit into the beginning of the space age. This is the late 50s, the early 60s. When the bottom right, the United States recovered a number of V2 rockets, and some of them were put at the for scientific use at the Naval Research Laboratory in Washington. So with these rockets and subsequent rockets of their own, they built instruments to observe the sun. And so what they were after is that since we had good belief that the corona was very, very hot, it should emit in X-rays. So the target here was to observe X-rays from the sun, and this is actually the very first X-ray image of the solar corona. So that's April 1960, and the camera is a pinhole camera, which means that it's just a hole in the hull of the of the rocket. The rocket kind of points to the sun, although it was a bit rotating, that's why it blurred. And the light gets onto a sensor inside the rocket. So this is the corona. And what is interesting is that the X-ray corona was bigger, or is bigger than the visible sun, which at that time was a result. People published about it, but now, of course, it's obvious the corona extends beyond the sun, and therefore the X-ray emission is bigger than the sun itself. It gets a bit more interesting if you compare that with other data of the time. And this is actually a sunspot drawing that was made here in the USET solar couple, similarly as we are still doing every day here. On April 19, 1960, it was cloudy, so there is no image. But April 20, I found an image, this one. And if you look at the details where you see this X-ray emission, that's where the sunspots are. The comparison is not absolutely one-to-one here because I'm actually not sure about the rotation of the image, but it looks entirely credible that these little dots here are the source of the X-ray emission. Just for the record, this drawing was made by Richard Gripping, which was a contractual here. It took like 200 observations that year, and together with André Kukelenberg, they were the only two observers at that time that covered the whole year. Very impressive. So let's go back to the X-rays. I was talking about the pinhole camera, so it's just a hole in the rocket with an aluminium foil to keep the visible light out. X-ray gets in, and because it's such a tiny hole, it naturally diverges again, and you can put in a sensor at the inside. So that's the simplest way of focusing you can do. But of course, the image gets sharper if your hole is smaller, but also less photons gets through. So it's not really comfortable to take images. Now, to take real images of X-rays is quite complicated because a natural lens will not focus X-rays, and also a mirror normally will not help because your X-rays go through it or get absorbed, but they don't reflect. The only way to reflect X-rays is to have them fall in on the mirrors, not in normal incidents, but in grazing incidents. So if they go at a shallow angle to the mirror, I don't have a mouse here, but there at the part that says reflecting surface, you can make them focused by some sort of paraboloid mirror, and that works nicely, except that you only have a very small aperture, and this little ring of your parabola where things get reflected. And to improve on that, people have been nesting one paraboloid into the other, and you get very complicated, heavy instruments, but they actually work. This is the mirrors of the XMM mission, not for solar physics, but for mainstream astronomy, let's say, which are plenty of these paraboloids, one after the other, until you fill up your complete aperture with reflecting surface for X-ray, all grazing incidents. Now, there was a time when solar physics could afford this size of instruments, and that was the time of Skylab, where solar physicists were building instruments like 5 meters or so. And so at the time of Skylab, this sort of technology was used, and they produced images that were very similar, actually, to what we have these days. I get an echo here. Shut up. The only thing is they had to bring this back to the grounds because it was taken on photographic film. They didn't have SIDC yet. So there are not that many images. This is one of the very few. And the situation would be somewhat hopeless to progress a lot if we have a couple of images per decade or so with these gigantic instruments. But there is where a new technology changed the game. In the business of the chip industry, they had to go to smaller and smaller etching of the microchips. And in the late 80s, early 90s, they were reaching the nano regime, where they needed to etch features smaller than 100 nanometers. And to do that, they could not do that with visible or UV that they had been using before, but they needed EUV to etch that precisely. And of course, to etch that precisely, you also need optics for that, and so there was a lot of effort spent into EUV optics. And as part of that, Stanford University developed multi-layer, which you see on the right here, which is actually just let's say a mirror surface that you coat with alternating little layers of two elements, molybdenum and silicon. One absorbs EUV strongly and the other one doesn't. And by tuning the number of these layers and the thickness of these layers, you can create a constructive interference pattern such that only one EUV wavelength is reflected and all the rest is absorbed. So this was a breakthrough. Now we could have normal incidence mirrors, perhaps not for X-rays, but for the extreme UV it is possible. And so this was experimented on a rocket, and indeed it works. And a few years later, this was put in a regular space mission on SOHO on the EIT telescope. Now, EIT was truly amazing in that it was conceived as a context imager for the spectrographs on board SOHO. So it was supposed to take a couple of images per day, and that's it, without much science topic of itself. Nevertheless, it was a giant success. It was the first space experiment in Belgium, one of the first paid by products. It was also the first to discover features like this, the EIT waves, which are sort of giant tsunamis crossing the solar disk in less than an hour. It was also the project in which I found my first job, so actually here at the Observatory, so I'm very attached to it somehow. And what is also interesting is that the team behind Jean-Pierre de la Boudinière of this instrument, it's still the team that we are collaborating with now on a regular basis in all the subsequent projects. No matter that it was a big success, it also had annoyances. Since it was originally a context imager, it was not made to make movies. And so this cadence you see here, that's about an image every 12 minutes. It's the absolute maximum this telescope could do, actually the computer of the telescope. And since these events, they last on the order of an hour, you essentially get less than a handful of images per event, which is nice to see that the event happened and you can study it a bit, but you cannot do actual dynamics, you cannot study motion, acceleration, or all of that. It's just not enough data. For that reason, in 2003 or so, we proposed to build another EUV imager, a miniature this time, less than a shoebox, you see at the bottom left, on a technology demonstration platform, Proba2. I guess most of you have heard it. This is the SWAP telescope, which roughly does the same thing as EIT, but 1 or 2 orders of magnitude faster and only in one wavelength. So it doesn't have the 4 wavelengths that EIT had. Now, how does it work? It's a little shoebox. Light comes in from one side. It has a little door that opened once in 2009 and it's open since then because we cannot reclose it. The light goes inside the telescope up till the first aluminium filter. Up to there, well, there all the visible light is kept out, this 1,000,000 times brighter thing than the corona. And only the high energetic EUV and X-ray goes through. Up till the primary mirror, which is coated by these multi-layers that I explained. And so it reflects this one particular wavelength that we have chosen. And the same thing on the secondary mirror, which is also coated, and then eventually it goes on to the detector. And the detector is an APS detector. That was a big thing. It was the first APS detector in orbit, in space for science. And if you don't know, APS is like kind of a successor of CCD detectors. It's the one that is also used in your mobile telephones. And it's in your mobile telephone because it has the advantage of consuming way less power than a CCD. It's also more robust against radiation. That's also good for the space project. But the big thing here is it's actually Belgian technology. This was developed in Belgium, and that helps us because the funding agency, products, Belspo, whatever, they are eager to pay Belgian companies and not so much to pay foreign technology, let's say. So there is a technological reason, but also programmatically it helped a lot. Not sure why I'm saying that, but anyway. So let's go back to the solar physics. SWAP, has a bigger field of view than previous telescopes, certainly bigger than EIT. And that was a sort of an accident because in the course of the project, we replaced this famous APS detector by a new generation of it. And the new generation was very similar, just a little bit bigger. And therefore, we do have a bigger field of view than what was originally intended. Towards the edge of the field of view, the image quality is not as good, but that doesn't matter because there are no fine features there anyway. And the result now is that we see that, and this is, I can say first, I think, of SWAP, is that the corona is way bigger than we thought in the UV. So people were thinking of that a sensible field of view for an UV imager would be like this SDO field of view, which capture most of the dynamics. But actually, if you see the SWAP field of view, that's up till here, and we can go image even further by doing off pointings, there is actually a signal that you can follow way further. And so that's kind of interesting because it's new and unexpected. And as you will see, there is physics there. And so the goal of matching the coronagraphs and filling in this occulter was successful with this new technology of EUV imagers that can fill in the black hole where the occulter is. In this particular case, which was the USET campaign, or the campaign led by French colleagues, I forget the number now. Yeah, that one, yeah. So it's data from that campaign. And you see that the event on the sun, this eruption here, triggers features that you see in the corona, in the coronagraph images. So that's what we were after. On the other hand, if you're a bit more critical, it doesn't work actually so good. Our field of view of SWAP is not big enough yet. We have to off-point here to the right to kind of make it to the coronagraph field of view. Also, where the two touch, you see that the SWAP image is extremely noisy. There is hardly any signal left there. It's clearly not good enough yet. And also the structures don't match really well. If you try to follow the lines you see in the coronagraph and the lines you see in SWAP, there is a sort of a connection, but it's definitely not one-to-one, and it's definitely not easy and nice. So there is something that we are missing, that's something that is not good yet. So let's take a step back and compare this EUV imagers and the coronagraph images and think about why they're different. In this case, they're both colored blue, but the blue is an artificial color, of course. It doesn't have anything to do with the feature itself. These are all black and white images, and we color them just for presentation. But if you think of how these are made, these images, there are differences. So on the left, I put a schematic of the EUV telescope, and the one feature there is it filters one particular wavelength that corresponds to a certain ion in the corona, which is formed at a certain temperature. So the EUV telescope, it will only show you features and dynamics that are at a certain temperature. The coronagraph doesn't do this temperature selection. It's covering a broader range of temperatures. The UV telescopes is actually imaging where ions are, where the coronagraph images where electrons are. Now in the corona, these things tend up to be in the same places, otherwise you have an electric field that nature doesn't like. So they're in the same place, but the process is different. In the case of the ions, it's emission lines. So it's two ions bumping into each other and releasing in a UV photon that we capture. This bumping together means that you need two of them, so it's proportional to density squared. While in the coronagraph, it's visible light that reflects on single electrons. So it's also proportional to the density, but not to the square of the density. This difference makes that what you see in the UV telescope is best seen close to the disk, but as the density drops off, your signal drops off with the density squared, it quickly goes to zero. While in the coronagraph, it's proportional to the density, so it doesn't drop that fast to zero, and the coronagraph is better further off from the disk. In both cases, the signal is summed up along the line of sight, But there is another geometric effect in the coronagraph, is that this reflection on electrons, it works best in 90 degrees in rectangular angles. And the geometric places where that happens is on a sphere. It's called the Thomson sphere. That's where you're most sensitive to the plasma. So if you sum this all up, it's actually no surprise that the images look somewhat different and that structures don't match really well. You're seeing the same plasma, but through different mechanisms. It cannot be the same. Besides that, there is also signal-to-noise problems. Here I've put again swap at the bottom and coronagraphs on top, and it's a polar view, as we call it, which is the solar surface is stretched out horizontally, right? You have like a landscape. You will still see the events going up and down. You see the structures kind of matching, but in between there is this region which Andrea started calling the gap, and I take this nomenclature, where the coronagraphs are only starting to come in at poor resolution, and often with lots of diffraction artifacts, and the UV images are extremely noisy or there's simply no data. That's the gap. This gap contains features that are actually interesting. Here you see a time sequence, and each next step is about half a solar rotation further. You see this on the top left, you see this big ear, which in the next picture is on the right. So that's when the sun is rotated. So you're actually seeing several solar rotation here with this big ear near the region of what we call the gap now, persisting. So this is truly amazing. It's a big structure that we thought was not existing in the solar coronas. SWAP saw this for the first time. And what is particular about it, it lasts so long. It lasts way longer than any active region on the sun. You see the sun is completely different every time, but still this feature exists. So it's apparently something of a giant structure of the corona that is retained. And that is interesting. Speaking of giant structure, also our magnetic field extrapolations, top left hit there. In this region, the gap region, is where they are either bending backwards into the corona, and then you have a loop, or they're bending outward into the solar wind. This is the area where it's not a magnetic field anymore dominating the structure, but it's the outflowing solar wind that becomes the strongest force. So this is where things change. And actually that region where things change is what we are supposed to put into these heliospheric models like Euphoria, and that drive our simulation of the whole heliosphere. So anything we do wrong in this pinker area gets propagated throughout the whole simulation, and we have wrongness throughout the whole heliosphere. So it's critical to do this right, otherwise the rest is also equally wrong. There are also physical reasons why this region is interesting. In this plot, I show distance from the solar surface on horizontally, from solar surface on the left to where we are at Earth on the right. And this U curve, that's the solar wind. So the solar wind gets accelerated in this gap region. Already a bit before, a bit afterwards also, but this is the main place. It's also the place where the solar wind goes through the local stand speed, the blue line. So in the middle of this gap is where the solar wind becomes supersonic and the equation starts behaving hyperbolically. There is also the Alfvén speed on top. The Alfvén speed keeps on, it's much higher of course, keeps on going down till much further, but it's the point where it reverses. It gets weaker and weaker as the magnetic field is not so strong anymore as the plasma pressure. So this gap is where physics happens. I'll let you read this for a moment. It so happens that some time ago we were having a team building day, and one of our collaborators asked me what should be a good strategy to choose future research topics. How do we know what will be hot in the future? What will be good to study? That's sort of my job as a team leader to give guidance. And at that time I had zero clue. But when making this presentation and thinking about this thing, maybe we've been looking too much and too long where our data is good maybe we should now look elsewhere and start looking where the data is not good. And so this gap is where things are happening, where physics is occurring, and where we don't have good data yet. And so let's do something about it. And in the next two parts of this presentation, I will be very quickly introducing our current projects that we are working on. So one of the two is the giant ASPIICS coronagraph, Robot 3, led by Andrei Zukov, which is the sort of coronagraph I've been schematically explaining before. But now we take it to the extreme with this external occulter, and we put it on another spacecraft that flies off hundreds of meters. So by putting this occulter really far away, we solve lots of the problems that are associated with it. This diffraction, this reduction of the signal, all that. This is a sort of technology demonstration, meaning that ESA has not done it before and is not sure how to do it, but we are studying and improving, and perhaps we will succeed. And the constraints are amazing, actually. The two spacecrafts will fly 150 meters apart, and the accuracy on that has to be 1.5 millimeter. This is amazing, very strong, but it's only a technology demonstration for the much harder thing that comes afterwards, where they want to use the same technology to have an X-ray telescope, where you have the sensors on one spacecraft and the mirrors on another spacecraft, and you need to be within accuracy of nanometers, right? So this is the easy game, but it fits our science. Having said that, it's still amazingly difficult to do science with it, because what I was showing you, that this external occulter creates a diffraction pattern. You can partially correct for that by software, since if the occulter is attached to your telescope, the diffraction pattern is always the same. So you study it, you analyze it, you model it, and you subtract it from your data, and hopefully you can go further. In this case, the occulter is free-flying, so it's not attached to your telescope, and every one of these millimeters that it's wrong, or arc seconds, I don't know what, your diffraction pattern changes. And so this is an active field of research, looking at Sergey here, to actually model this and to take in the position and directions of the two spacecraft and forecast, model what the diffraction pattern should be in that case. So also that is technology demonstration. ASPIICS will bring us much closer to the sun than ever before. The red curve here is the LASCO C2, the red coronagraph that I showed before. Inner edge, so inside the red circle is all blackness in C2, the best, let's say the reference coronagraph now. And so ASPIICS will go down to the blue circle, much deeper in. At the bottom right, you also see the same graph explained as spatial resolution. So where ASPIICS will go way deeper in, horizontally, in radial distance, but will also come much lower in spatial resolution than previous coronagraphs. And so this annoying gap here between the EUV imager and the LASCO C2 coronagraph will be filled with ASPIICS. I'm not going to say more. ASPIICS could be discussed in 3 other full presentations, so there's no time for that. I'll quickly jump to the second big project that the SIDC team is involved in. It's the EOI telescopes and Solar Orbiter. Solar Orbiter is not a proba, it's not a technology demonstration thing, but it's a mainstream science mission of ESA. And this will actually fly to the sun, into the Mercury orbit, and will also have polar view. So it's more like a planetary flyby, it's just that the planet is the sun. And on that mission, our team will be involved in the extreme ultraviolet imager telescopes. These are 3 telescopes. PI is Pierre Rochus from CSL until it's being taken over here. And I'm sorry, I can't show nice pictures, so this is a boring graph. So on the bottom graph, you see horizontally time in years, and vertically the distance to the sun, and the red line is where the spacecraft will be. So it makes this dips back and forth into the corona. deep into the orbit of Mercury during a couple of perihelion, and each time of those we will have very high resolution images and in situ measurements. The top graph is the other dimension. It's with respect to the solar equatorial plane. You can think of this as the ecliptic. It's not exactly the same, but almost. So we make excursions to the North Pole and to the South Pole. Not very far, it's only 35 degrees or somewhat less. But that will help us to have a look over the pole and get, for the first time, a view there. So I already said, EY is 3 telescopes, 2 high-resolution telescopes, and 1 full sun imager. And this is the full sun imager. It will have a field of view of actually 4 solar radii. Yeah, that's correct. So 1 solar radii on top of the one that you have from the disk center already. And it can off-point, and we'll have a little occulter, which is a novelty here, an EUV occulter. And it's actually sort of an experiment in itself. It's basically the telescope door that is closed half. But that could already help in getting more signal further away in deep exposures. So I don't want to say too much here, just that this is ongoing. There are higher resolution images also here. This is where the thing was 2 months ago. This is what I call the shipyard. In the middle you have the spacecraft, and on the left and on the right you have coat racks with equipment, all kinds of instruments, and EOI, our telescopes, were in the top oval. They were removed just before this image was taken, so it's on the spacecraft now, I presume, while our electronic box is not yet. So this is a very intensive phase now for the spacecraft people to put everything together, and the launch is aimed at 2019, which looks hypercritical to make it. It will probably slip a bit or more. So that brings me to my conclusions. I hope I gave you a convincing overview that the corona is not only big and hot, but also interesting. The main problem with observing the corona is that the sun itself is 1 million times brighter, so you must get rid of that signal somehow before you can see the corona. Coronagraphs solve that with their occulting disk, and UV imagers solve that by aluminium foil and these multi-layer coatings that only reflect the high temperature emission, let's say. These 2 solutions work nice on their own. If you combine them, it's even better, but still there is it doesn't match very well. There's a fracture zone in between, and exactly in that fracture zone we believe that the physics of space weather is originating. So there is things to be addressed there, and we are actively preparing for that by building new instruments that will go and see exactly there, which are the ASPIICS coronagraph on Observatory and the EY telescopes in Solar Orbiter. And with that, I can only say that the take-home message should be that we have to think about the gap in between. Thank you.